Thank you, Anna, for the introduction, and thank you to the organizers for putting together this wonderful conference and inviting me. So today I'll be telling you, well, actually, about some work that was done a couple of years ago, but I think it's been sort of flying under the radar and sort of seeing experiments emerge. It seems to me that this might actually be highly relevant. So my aspirations for this talk are twofold. First of all, I hope to bring to the attention of the experimentalists in the audience a theory paper which they might find useful. But also, from my perspective, I think there's a number of extensions of this work that I could do, if there was motivation. So I'm also hoping that, maybe you'll tell me there's something that's sort of related to this, so then I could do something that could be useful to you. Okay, so let's begin the talk. Without further ado, I should say this is work with Sarangapala-Krishnan, who maybe is in the audience, or maybe he's still having, there he is, right? And yeah, I'll also say that if you have questions at any point during the talk, don't feel like you have to wait for the official question and answer session at the end. Feel free to interrupt and ask. Just remember, I do have a big stick. Okay, so what's the setting that I'm going to be considering in this talk? The basic setting is we'll be considering systems of quantum dipoles. So by a quantum dipole, I mean essentially I have a two-level system which is well localized in real space. I have lots of two-level systems, and two-level systems interact with each other with an interaction that decays with distance as 1 over r cubed. Yeah? So 1 over r cubed is the decay of the standard dipole-dipole interaction. So it's two-level systems that interact like dipoles, right? Either electric dipoles or magnetic dipoles. Now, quantum dipoles of this type are ubiquitous in nature, right? They show up in all sorts of places. They show up with polar molecules and optical lattices, interacting with electric dipole-dipole interactions. They show up with NV centers in diamond. They show up for dipolar quantum magnets, interacting with magnetic dipole-dipole interactions. They show up in nuclear spins. They show up in, for the low energy excitations in the electron glass, any number of different microscopic platforms which can be described in terms of systems of quantum dipoles. And for the purposes of today's talk, I'm essentially agnostic as to what the underlying materials platform is. I don't really care if you're dealing with nuclear spins or polar molecules and optical lattices or NV centers in diamond or what have you. They're all systems of quantum dipoles, and my theory will apply to all of them. My requirement, though, is that I need a system of quantum dipoles with very strong disorder. Yeah? So sort of strong randomness, strong inhomogeneity, so that the system is extremely close to localization. Yeah? Like, you might think that, well, if disorder was infinitely strong, then each dipole is completely decoupled from every other dipole. So if you imagine applying random fields to the dipoles, and you draw the random fields from a distribution that's infinitely wide, then each dipole has a different infinitely strong field applied to it, and that decouples it completely from all other dipoles. Yeah? But if you back off from this crazy infinite disorder limit, then the fact that you have this 1 over r cubed long-range interaction means the problem can't actually be localized, yeah? But it can be close to localization. So the dipoles will be able to interact and relax through the 1 over r cubed dipole-dipole interaction. And this talk, yeah, Anna Maria.
Localization is not in motion, so the dipoles are frozen in space, and the localization is not.
The localization, right? So I'm talking about, the either thermal localization, so whether heat. Yeah. So flip-flops are one of the mechanisms by which localization can be broken. So I'm talking about whether, if you have a single dipole initialized in a particular spin configuration, does it stay in that spin configuration forever? Or, does it flip or sort of move somewhere else? So it's, localization, delocalization of either the spin excitations, if there is a conserved sort of spin U1, or if there's not, then just heat. So now we're working sort of close to localization, but it's not actually localized because of the 1 over r cubed interaction. And we'd like to quantify how it is. Okay? Furthermore, we're going to be working close to a low entropy state. So what do I mean by a low entropy state? Well, the canonical low entropy state would be zero temperature, yeah? So zero temperature is also zero entropy, and by low entropy I mean that the temperature doesn't have to be zero, but it's small, yeah? That's one possible choice of low entropy state. It's not the only one. Another possibility is I could work close to maximum polarization. So if I had, let's say, a conserved SZ, then I could apply some big external uniform field, polarize the system so that every spin points along Z, that's maximum polarization, that's a low entropy state, and then I could allow the magnetization to change a little bit so that, it's not perfectly polarized along Z, but it's close to perfectly polarized, and that would be another example of a low entropy state. And if I did it that way, then I wouldn't need to be close to zero temperature. I could be at infinite temperature, but sort of close to maximum polarization. Yeah? So it's strongly disordered quantum dipoles close to a low entropy state. And the final requirement is I want to work in 2 or 3 spatial dimensions. Yeah? So I'm not going to talk about dimensions 4 or more, for which I will make no apology. And I'm also not going to talk about spin chains. So dimensions 2, dimensions 3, or you could also consider sort of thin films or slabs, which would interpolate between my 2D and 3D results. And that's the basic setting in which this talk operates. Now, yes, Ash.
One question, so is the disorder just in the local fields or also positional disorder?
Yeah, so it doesn't really matter as long as it's strong. So you could put it in the local fields, you could make it positional, you could also have your disorder be only positional. So for something like the electron glass, the natural disorder types would be purely positional. And yeah, it doesn't really matter, and it's the same theory of relaxation in all of those cases. So there's this theory of relaxation which cares about a small number of things, but at the end of the day it's agnostic to microscopics. What are the inputs to the theory? Well, there's a handful of inputs. So yeah, okay, what are we going to study? Well, we're close to localization, so if let's say we had random fields and each field was infinitely strong, then each dipole would be completely detuned from all others, and each dipole excitation would live forever. You would initialize each dipole in a particular spin state, aligned with the field, and it would just stay like that, forever. Now, because of the 1 over r cubed interaction, that's not actually going to be the case at any finite disorder strength. So the dipole spin state will relax, and we're going to be studying the relaxation coming about from the dipole-dipole interaction. Yeah? And we're only going to be studying the relaxation coming from the dipole-dipole interaction. So, I will not be describing relaxation due to coupling to phonons or relaxation due to coupling to any sort of environmental degrees of freedom. Yeah? It's only the intrinsic relaxation from the dipole-dipole interaction. And I'm essentially assuming that that's my dominant relaxation mechanism. Given that, we're studying relaxation from the dipole-dipole interaction, there's 2 possible timescales. So the first is the bit flip timescale, which I'll call T1. Yeah, so this is the timescale on which a particular dipole initialized, let us say, with spin up, might end up flipping to spin down. And it's the typical T1 time or the typical bit flip time. And then there's also the decoherence timescale, which I will call T2. So the decoherence timescale is the typical timescale for decay, let us say, of spin echo. Yeah? And you can measure this in an interferometric experiment, like some double electron-electron resonance type experiment, or you can measure it in pulsed nonlinear optics, as was done in this paper here. So this is using the technique of multidimensional coherent spectroscopy, which is a technique that's originally taken from chemistry, but can also be applied sort of outside of chemistry. Yeah? Okay, and the question of interest is we have these 2 timescales, T1 and T2. How do those depend on tuning parameters such as, let's say, the excitation frequency of the dipole that I'm considering? Yeah, so I have 2-level systems. They have some splitting omega. How do the timescales T1 and T2 depend on that energy splitting, h bar omega? Or, for instance, how do they depend on temperature if I'm working close to low temperature, or magnetization if I'm working close to maximum polarization? What are the inputs to the theory? Well, there's actually only a handful of inputs. So the first input is spatial dimensionality. So I said that I was going to work in either 2 or 3 dimensions, and whether it's 2 or 3 matters, yeah? So I care about the spatial dimensionality of my system. I care about the excitation frequency, so you have a 2-level system with energy splitting h bar omega, and what omega is matters, the temperature matters, and then the final quantity that matters is the low energy density of states. Yeah? So I have a bunch of excitations, 2-level systems with energy splitting h bar omega, and how does the number of 2 levels, how does that density of states of those 2-level systems depend on omega? And I'll characterize it very simply as the density of states goes like omega to the power gamma minus 1. Now, I have my reasons for this somewhat bizarre parameterization, and there's essentially 2 qualitatively different behaviors. So the first possibility is we could have gamma equals 1. So if gamma equals 1, then the low energy density of states is frequency independent, meaning I have a constant low energy density of states, or at least constant up to logarithms. And this is the sort of thing that you would naturally get in sort of fermionic systems. Yeah? The other possibility is that gamma is bigger than 1, and if gamma is bigger than 1, then the low energy density of states vanishes at low frequency. Yeah? And that's what you would naturally expect in bosonic systems. So in bosonic systems, stability requires that the low energy density of states should vanish, because if you had a non-vanishing low energy density of states, then you could both condense into some low-lying excitations, and that would give you an instability of the ground state. Yeah? So typically in fermionic systems, we expect constant low energy density of states up to logarithms, and the logarithms are dealt with in the paper, but I won't talk about them in this talk. Or you could have a vanishing low energy density of states in bosonic systems. And in fact, there's a universal prediction from Gurari and Choker, which says that for bosonic systems, gamma should be 5. You can mentally put gamma as 5 in there if you want, but I'm perfectly happy to treat gamma as just a phenomenological parameter, and all I really care about is it 1, meaning constant density of states, or is it bigger than 1? So those are the inputs to the theory. What are the outputs? The outputs are scaling predictions for T1 and T2, how these depend on frequencies and temperatures, and these predictions are universal in the sense that they're platform independent, and they only care about this handful of inputs, like spatial dimensionality, and like whether the low energy density of states vanishes or not. One thing I want to emphasize, because this has sometimes been a source of confusion, is that relaxation rates are not the same thing as AC conductivity. Yeah? And the easiest way to illustrate this, again, is to take the sort of trivially localized limit. Let's consider an Anderson insulator. Relaxation rates in the Anderson insulator are 0 at all frequencies, right? There's excitations at arbitrary frequencies, and none of them relax if you just have a non-interacting Anderson insulator. But if you look at AC conductivity in the Anderson insulator is omega squared. That's Mott's law. Now, relaxation rates and AC conductivity, not the same thing. So this is a sort of new quantity that we're computing about near localized systems, and it's now experimentally accessible. Okay. Let's start by discussing systems at strictly 0 temperature. Yeah, we'll move to low but non-zero temperatures in a bit. So let's start at 0 temperatures. And the basic strategy is, you start by sort of pretending that your system is localized, which it would be in the infinite disorder or 0 interactions limit. And then you look for resonances. So you turn on the interactions, and what interactions can do is, it could be that you have one possible configuration of the system, and another possible configuration of a system, and a third configuration of the system, and so on. And interactions could take you from the first configuration to the second, the third, and onwards. Shamir?
Maybe can you give us 2 examples to Hamiltonians, just to be sure that we don't get lost?
So the simplest would be you could take S dot S interactions with 1 over R cubed coefficient and random fields on every spin.
Okay.
That's an example of a model Hamiltonian that does what I want. And spin 1/2. Okay, so then we're going to look for resonances, and by a resonance I mean so you can imagine constructing the new eigenstates, starting with the localized eigenstates, trying to construct new eigenstates in perturbation theory. When you do perturbation theory, you have matrix elements in the numerator, energy differences in the denominator. If the matrix elements are all small compared to the energy denominators, then perturbation theory is convergent and you stay close to the localized state. Resonances are places where this is not true, and the matrix elements are big compared to the energy denominators, and they're sort of what give rise to instabilities of localization. So there's a very simple geometric counting you can do. If you have a ball of radius r, then you have r to the d states, or a volume's worth of states, single particle states. So the smallest energy denominator you can find between a volume's worth of single particle states goes like 1 over volume. In contrast, the matrix element falls off as 1 over r cubed. Now, if you're in 2 dimensions, then the matrix element falls off with distance more rapidly than the energy denominators do. Which means that if your disorder is strong enough that you don't have resonances at short distances, then you're not going to have resonances at long distances either. And then you're safe. So in 2 dimensions, at 0 temperatures, you can be truly localized, and if you're truly localized, then the relaxation rates are 0, or the relaxation times are infinite, or in practice they're set by phonons or some external environment or stuff that's not in my theory. Okay. In contrast, if you're in 3 dimensions, then energy denominators fall off as 1 over r cubed, and matrix elements also fall off as 1 over r cubed, so they both go the same way. How should I deal with this? Again, we start from the assumption that disorder is strong enough that you don't have resonances at short distances. And then the way you should handle this was sort of explained by Levertov in 1990. What you do is you do an integral over radial shells, and the integral over radial shells gives something that diverges logarithmically with the distance up to which you've looked. Yeah? So this is the probability of a resonance, and the probability of a resonance, if you look out to length scale r, goes like log r. Log r is unbounded, so what this means essentially is that you're guaranteed to have resonances. And just because you were safe at short distances doesn't mean you can pack up and go home. Look at long enough length scales and there will be resonances which give rise to an instability of localization. Okay. What does this do? Well, first, let's consider the situation where we have a constant low energy density of states. So if you have a constant low energy density of states, then integrating out excitations with energy greater than omega, that yields a system with a characteristic density that's omega. And if you have a characteristic density that's omega, and you're in 3 dimensions, and the typical length scale between spins is 1 over cube root of that, so the typical length scale is omega to the minus 1/3, and you substitute that into the 1 over r cubed matrix element, and you get a characteristic matrix element, and therefore a characteristic relaxation time that goes like this, linear in omega. Yeah? And this is what was observed in the electron glass experiment in silicon. Okay, then there's the other possibility, which is you have a vanishing density of states. If you have a vanishing density of states, then there's extremely few excitations available at low energy, so you really need to use the log. Yeah? So essentially your condition for instability of localization becomes that the density of states times this log factor is of order 1. And what you get from that is you get resonances appearing at a length scale which is exponential in frequency. Yeah? So log r is omega, so r is exponential in omega. And if you substitute that into the 1 over r cubed dipole matrix element, you obtain a relaxation rate which has an essential singularity, and it diverges exponentially fast as omega goes to 0. So you have very different behavior depending on whether the low energy density of states vanishes or not. If it doesn't vanish, then the relaxation rates are just linear in frequency. If it does vanish, they're exponential in frequency in 3 dimensions. All right, so thus far, what have we calculated? We have calculated the typical bit flip rate, 1 over T1. In this case, we're at 0 temperature, so 1 over T2 scales the same way. And in 2 dimensions, the bit flip rate is just 0 if dipole-dipole interactions are my only relaxation channel. And in 3 dimensions, it's linear omega if the low energy density of states is non-vanishing, and exponential in omega if the low energy density of states is vanishing.
These are all sort of fairly golden rule estimates.
You would get identical estimates from Fermi's golden rule.
We don't know
Yeah.
anything about initial state, we don't know. It is just something from a typical state.
It's just a typical golden rule estimate. Yep. Yeah. I mean, you can do it one of two ways. You can either do it as Fermi's golden rule, or you can view this as a hopping problem with a certain hopping matrix element, which gives you the timescale for hops.
But you have accepted because this was seen in the experiment by Armitage, right?
For the linear omega was seen in the experiment by Armitage. You know, the exponential thing for vanishing density of states, that nobody has done the experiment yet, as far as I know. But maybe somebody in the room could. Yeah. Okay, now let's move to non-zero temperature. So once we go to non-zero temperature, there's a new relaxation channel that opens up, first identified by Burin in 2005. So the Burin channel is a flip-flop channel, which Anna Maria asked about. So the basic idea is, okay, if you have a bowl of radius r, it has a volume's worth of dipoles, which could participate in a resonance, pick one of them and see if it can flip-flop, meaning one dipole goes from up to down and another dipole goes from down to up. And ask if this sort of flip-flop two-body process can be resonant. Now, any given dipole has another volume's worth of dipoles which it could flip-flop with. Yeah. So the total number of possible flip-flop processes goes like volume squared. Yeah. The matrix element is still 1 over r cubed. Yeah. So now you're comparing 1 over r cubed to a volume squared phase space. And so the energy denominators of flip-flops fall off as 1 over volume squared, whereas the matrix elements only fall off as 1 over r cubed. And if d is 2 or 3, then 2d is bigger than 3, so the energy denominators fall off more rapidly than the matrix elements, and so you're guaranteed to have these flip-flop resonances at any non-zero temperature in spatial dimensions 2 or 3. Okay, now just from this sort of comparing the phase space to the matrix element, you can get a characteristic resonant length scale, and that characteristic resonant length scale is a power law function of temperature. And if you substitute that into the dipolar matrix element, you'll get a Fermi's golden rule type time scale estimate, which is the Burin time, and the Burin time is also a power law function of temperature. Okay, so that's the Burin time, but I wasn't after the Burin time, I was after T1 and T2. Yeah? So how are T1 and T2, which are the sort of physically relevant quantities of interest, related to this timescale that comes out of the Burin argument, T Burin? Okay, let's start in 3 dimensions, where the answers will be relatively straightforward, and then 2D, where they will be considerably richer. So if we're in 3D, then thermally activated spins have density this much. Yeah, this is just integrating the density of states up to temperature, or up to frequency kT. Here's my length scale from Burin's argument. If I take this length scale and do 1 over length scale cubed, I get a typical density, which scales the same way. Yeah, so this is the density of Burin resonances. The density of Burin resonances scales the same way as the density of thermally excited dipoles. So what that tells me is that a temperature-independent fraction of the thermally excited dipoles are participating in these Burin resonances. Yeah? So sort of order 1 fraction of the thermally excited dipoles can flip-flop and delocalize in this way. And so that being the case, their typical T1, well, surely I get more time because we had questions during the talk. Yeah. So that being the case, the typical T1 should be essentially just the same as this Burin calculation gives. So the typical T1 is just T to the minus gamma, and then the typical T2 is set by the excitation with the nearest thermal excitation, which goes the same way. So T1 and T2 both scale like some simple power of temperature. Okay, that's 3D, where I said everything was simple. Now let's move to 2D, where the behavior is considerably richer. 2D, I still have guaranteed resonances by Burin's argument, and the time scale looks like this. But that's not the bit flip time scale of a typical dipole. And the way to see that is, well, the thermal excitation density is still T to the gamma, but now the density of Burin resonances is T to the 2 gamma. Yeah? And if temperature is small, then T to the 2 gamma is small compared to T to the gamma, so only a very small fraction of the thermally excited dipoles can participate in these Boulder resonances and flip-flop. Yeah? Most of the dipoles cannot. And as I take temperature to 0, a fraction 0 of the dipoles are actually participating in resonances. Okay, so how to deal with this? Yeah, so the typical bit flip timescale will be considerably slower than, or considerably longer than the timescale that comes out of the Boulder analysis. And to get it right, we need to take account of what's called spectral diffusion. So what's spectral diffusion? Well, you have a bunch of little dipoles, yeah? But each dipole is interacting with all the other dipoles, and some of those other dipoles are flipping, yeah? And when those other dipoles flip, they generate electrostatic, or if you wish, magnetostatic energy shifts to the splitting of the other dipoles, yeah? So all of the dipoles, they have a splitting which varies over time as there's some background flipping going on due to these Boulder resonances, and that's the phenomenon of spectral diffusion. Yeah? Now, how do we deal with this? Well, I'll show you a very quick and dirty argument. If it makes you uneasy, don't worry. You can do a sort of much more careful, self-consistent argument, which is in the paper. It's just too involved for a talk. So I'll give you the quick and dirty version. And the quick and dirty version is this, that you have thermally excited dipoles at density T to the gamma, and you have Boulder resonances at density T to the 2 gamma, which means that a fraction T to the gamma of the thermally excited spins are Boulder resonant. And because of spectral diffusion, the identity of the thermally excited dipoles which participate in the resonance network keeps changing. So you have spins which randomly cycle in and out of the resonance network, and at any given time, a fraction T to the gamma of them are resonant. So roughly speaking, each spin spends a fraction, T to the gamma of its time on the resonant network. When it is on the resonant network, it flips at the Boulder rate, which is T to the 3 gamma. Yeah, so it flips at this rate when it's on the resonant network. It spends that fraction of its time on the resonant network. Multiply those two things together, and you end up concluding that the rate at which a typical spin flips is T to the 4 gamma. So this is the bit flip timescale. If you want the dephasing timescale, that's set by the typical interaction with the fluctuating network, and that's T to the 3 gamma. Yeah? So you put these two things together, and you conclude that the T1 and T2 times scale differently. They're both power law functions of temperature, but different exponents, which means there's a parametric separation between the T1 and T2 times, and this parametric separation gets broader as you take temperature to 0. And in fact, this has also been observed, this parametric separation, in diamond NV centers in 2003. So what these guys did is they measured T1 and T2 times in diamond NV centers, and they saw that they were sort of orders of magnitude different, which is something that we had predicted, and they were working with a 2D system, thin film. What they did not do was change the temperature and see that things scaled the way we predicted. But, I would love for them or somebody in the audience to do that experiment and see if they can actually sort of verify not just the parametric separation, but also the scaling predictions for how T1 and T2 behave with temperature. In principle, you can also consider, I've talked about 2D and 3D, you could also consider slabs, yeah, of finite thickness. So those would interpolate between 2D and 3D behavior, essentially depending on whether the resonance length scale is big or small compared to slab thickness. So there's a bunch of crossovers. In principle, T1 and T2 can cross over at different temperatures, and I'll just refer you to the paper for details. So to summarize, what have we come up with? Well, we have a universal theory for typical relaxation rates of strongly disordered dipoles in dimensions 2 and 3 at temperatures 0 or low but non-zero. And many of the key predictions have been confirmed in an experiment. Now, some experimental outlook. Well, in 3D with non-vanishing density of states, we had a prediction which has been observed in the electron glass. At 3D and vanishing low energy density of states, we had a much more dramatic prediction, which nobody's gone and looked for yet. So I would hope that somebody will. At 2D, we had this prediction of a parametric separation, which has been observed, but we also predicted, how things would scale with temperature, and that's not been checked. So I'd hope that somebody might be motivated to check it. But there's also an interesting theory outlook. So in the version, in what I just told you, we computed the typical relaxation rates. We computed typical T1 and typical T2, but for a disordered system, there's much more than just what the typical thing is doing. In principle, there's a full distribution. So one could ask, what does the distribution of T1 times look like? What does the distribution of T2 times look like? And I think that's something that certainly could be computed in principle, if anybody was motivated to do the experiment. And equally, I've just characterized the relaxation of the dipoles by one time scale. Yeah? And characterizing the relaxation of the dipoles by one time scale is equivalent to saying, okay, I have some spectral line, what's the line width? Yeah? But in principle, I could also ask about the full line shape. It's probably not just Lorentzian, yeah? Or the time decay is probably not just simple exponential. So again, like what does the actual line shape look like? I think that again is something that could be computed in principle, but like sort of if there's an experimental motivation, then this could be done. So like if you think you might be interested in sort of more quantitatively exploring relaxation of quantum dipoles, then I hope you will let me know. Okay, and that's essentially what I wanted to say. So this was work with Sarang, and I should also thank the experimentalists who got us into this in the first place with this electron glass experiment. And like now I'm happy to fully take questions.
Thank you so much, Rahul. Questions? Yeah, Hadise.
Thanks for the interesting talk. I just have a question. In the calculations that dimensionality appear at any place, you need to assume it's an integer, or I can kind of like, it's an analytic function. I can think that, for example,
I mean, in principle, it's an analytic function, and you could do it as a function of D.
Yeah.
I only work things out for integers 2 and 3, but if you have some setup which you think is described by fractional D, then
yeah,
surely.
I mean that, for example, you may have fractal dimensions. The reason is that like I noticed that the length, the scale that you talked about, so if you have like some dimensions, it may diverge. So then would you say that in that case, the separation, the crossover between 2D and 3D is non-existent?
Well, let's see. So I guess this will diverge when D is 3 halves, right, which is less than 2.
3/2 I don't have, but I think that like with a log 3/2 or like a square root of 2, you could kind of think about like fractal dimensions and kind of minimize the denominator so that can blows up. Right?
Yeah, I mean, that would be a crossover below 2 dimensions, which I wasn't talking about, but absolutely there could be some interesting, I mean, so I think there would still be relaxation. It would just come from other channels at non-zero temperature. But yeah, in principle, if there was motivation, we could absolutely look at fractional dimensions where this length scale grows up.
Yeah, thanks.
Jamir.
I do it from here, is it okay? No. You have to try, right? Yes, you don't have to do anything. What about phonons? So will not they alter significantly your scaling of T1, T2?
Right, so the question is, what about phonons? Well, okay, so there will be some, let's assume that we're talking about a material, so there are phonons, and an optical lattice, they're just not there.
Of course.
But okay, like if it's a material and there are phonons and there's some time scale on which your dipoles couple to phonons, and then like everything I was talking about gets cut off on that time scale.
But
so then this theory applies to timescales up to which phonons come into play. And yes, that could also have a dependence on frequency and temperature. But no, there's also some prefactors which could be, well, okay, we can guess what it is, right? So if it's acoustic phonons, their density of states will vanish as omega cubed. So that at least is going to, the time scale will at least go to infinity as 1 over omega cubed, and it might be faster, right? just based on density of states arguments. But then there's also some G squared, where G is the dipole to phonon matrix element, and that could be very weak, and it could have some temperature dependence. So this theory applies on the time scale where dipole phonon coupling is negligibly weak. And that's an empirical question.
Yeah, it will depend case by case, right? If you get cut off earlier or not, and how this thing will not be visible when you suggest someone to do it, right? That would be.
Yeah, no, it could absolutely be the case that phonons. Well, okay. So what you essentially need is that the time scale for intrinsic dipole-dipole relaxation is short compared to the dipole for the time scale for dipole phonon relaxation. Otherwise, you can't see anything.
You don't have in mind materials or situations where this will happen. You folks didn't think about it.
Well, okay. So I think there isn't a universal answer to that. Yeah, this depends on material parameters. But take the example of silicon, for instance, where the Armitage experiment is done. Like in silicon, empirically, it's the case that the phonon timescale is just long compared to the intrinsic relaxation time.
Okay.
Yeah? So you do experiments on silicon, and indeed, relaxation is dominated, by dipole-dipole interactions and not by electron-phonon. Now, maybe you look at some different material, and it'll be the other way around, and phonons will kill you before dipole-dipole interactions ever come into play. But that depends on materials.
Maria.
Thank you, Rahul. I just have a very basic question. So for me, T1 and T2, when you look at the relaxation, it's for a Markovian band, or what? For me, it typically depends on the spectral function of the band. So how I interpret the relaxation?
Well, there's no bath here, right? It's all internal. It's just.
Also, T1. So that's the part that I want to understand. T1 and T2 are relaxation because of what?
Because of dipole-dipole interaction. So the bath in question is self-generated. Because of one of our cubed interactions, eventually I'll have thermalization, and that's my bath.
I see. So there's okay, I see. Because that's the problem, perhaps, in many experiments, the relaxation comes because other sources of.
Right. So, this is related to Jamir's question. Of course, there's coupling to other degrees of freedom. This is just the dipole-dipole Hamiltonian. So, there's phonons, or there's cavity modes, or there's just leakage to the environment, and there'll be some timescale for that. And this theory is valid, up to that timescale.
Okay. So then my other question is that, but the dipole-dipole interactions are only flip-flops. So I don't understand why you said that only you treat flip-flops. What is the other type of interactions that you consider?
It's just. I'm just envisioning. You could envision just S dot S, right? And you could have anything.
Okay, so the first part was S dot S, and when you were saying
So at zero temperature, I'm just envisioning that, let's say I have a conserved spin component, call it SZ. So, and I have an upspin dipole here, and maybe that can flip to down, and the upspin hops somewhere else. Yeah. I suppose you could call that a flip-flop, but I'm reserving flip-flop for the case where I have two thermally excited dipoles, and so in this case, I don't require both dipoles to be thermally excited, right? I could have one dipole that's in the ground state and the other dipole that's excited, and the excited dipole returns to the ground state, and this ground state dipole gets
but this
flipped
is not. My confusion is that this is all what you have in dipole-dipole interactions. What is the other term?
Nothing.
No. Okay. So everything is just flip-flops.
Yeah. But so at zero temperature, it's flip-flops where only one of the dipoles is excited. And at non-zero temperature with the Buran mechanism, both of the dipoles in question are thermally excited.
Okay, so we can talk, but if you have one up and one down, that's the only thing that happens. Yes?
Okay, you have one up and one down, but up and down are not necessarily the low energy states if I have random fields, right? So let's think of them as two-level systems instead. And let's say, there's the low energy state and the high energy state. So at zero temperature, I'm considering processes where I have one dipole in the high energy state and another in the low energy state, and they're flip-flopping. non-zero temperature, in principle, they could both be in the high energy state, but maybe the interactions are different. But yeah, it is just flip-flops in that sense.
Okay.
It's more of a comment than a question. So about the effectively single particle case of zero temperature. So there is an exact calculation using a modified sigma model for 2 dimensions and 1/r², hopping.
Correct. This is a liner from 2000 and
yes,
something.
Which says that in the unitary symmetry class, there's a metal insulated transition, which is inconsistent with Levita's RJ. Did you look at that in 3 dimensions? Do you know if it
No, so I know the paper to which you refer. Yeah. I think that's particular to 1/r², and it's because, for 1/r² in 2 dimensions, there's a competition between 2 logarithms. There's the Levitov log, and there's the weak localization log. And I think, the sort of magic in that paper is from the competition between the Levitov and the weak localization logs. In 3D, there's no weak localization log. So I don't think there's anything analogous to that in 3D, nor do I, as far as I know, I don't think a liner has ever asserted there's anything analogous to that in 3D.
Well, log or no log, one can compute the beta function in the regime of weak disorder, and from that make a conclusion if that would be an unstable.
Yeah, but there's no, there's no, sigma model in 3D at weak disorder, at strong disorder, there's nothing, right? The Anderson insulator. There's no weak localization log in 3D, so I don't expect anything analogous to that with 1/r².
I don't see why we need the log.
I think that's where the transition you're referring to comes from. Yes, I'm aware of the paper to which you refer. Nonetheless, I assert that it is not relevant. That is a particularity of 1/r³ and 2 dimensions, and 1/r³ in 2 dimensions is an interesting problem. And maybe somebody wants to do.
I'm talking about 1/r³ in 3 dimensions.
Yeah, 1/r³ in 3 dimensions, I think, does not have what you're talking about. What you're talking about is very specific to 1/r² and 2 dimensions.
Okay, so I think Sarang wants to say something about it.
Just like a quick addition to this. So I think if you have 1/r³ in 3 dimensions, you do have what looks like a metal insulator transition, but it's a transition between the diffusive metal, the normal diffusive metal at weak disorder, and this subdiffusive critical Levitov state at strong disorder where Levitov's treatment is well controlled. So I think there is a transition between those states.
But it's not the aligner thing.
Yeah, it's different. The physics is different.
Right. Yeah.
Okay, so perhaps we can continue these discussions during the discussion session. Thank you so much, Rahul.